In this example problem, I'm going to talk about the relationship between force, displacement, work, and potential energy. So here's the problem. Determine the gravitational potential energy for all separations R, given that the gravitational force inside an object is given by this. So this is the formula. So envision, for example, the Earth, and Earth has a radius, capital R, and Earth has a mass, call it M1, but there's another mass which is inside of that, M2, and the center of mass distance from the Earth, M1, to this mass M2 is given by the vector R. And this is the equation for that force only when I'm inside of the Earth. So starting out now, we want to know for all separations. So we'll do this problem second. Well, first we'll think about the general case where the two objects are inside of each other, but they're far apart, like this. So we'll pick a system, mass 1 and mass 2, and we'll envision it that they're now not inside of each one's inside the other, but they're far apart. I have a mass 1, a mass 2, and that's my system. And I'm assuming that the surroundings is everything else. And assumption is that there's no other forces acting, that this is all there is the gravitational force between these two things. And so if I kind of draw a picture that I have my mass 1, my mass 2, I have the vector from the center of mass from 1 to the center of mass 2, I'm calling that my vector R. And that's shown in the initial position. And then I'm saying that my R direction, my unit vector R direction, is in that same direction as my R position vector. And then at some later time, and then the forces are acting, the internal forces, so generally designated by a small case f. So the forces acting onto by 1 initially is this way, and the forces acting on body 1 from body 2 is acting this way. And then at some later time, they're being pulled together, so the distance is less apart, and so now they're at some final time, the distance is shorter, and the separation distance here, r sub f, is a smaller quantity. So that's my position along the unit vector r direction, and so my change in r over time is the final r minus the initial position vector in r direction. So there's my initial, there's my final, so I think my final minus my initial, so my change in r is in this direction. So you can see that the change in r is acting in the minus r hat unit vector direction. And if you think about, we have some parts relative motion, you can, if I'm considering that my coordinate system always starts with the end of this position being at M1, you can think of the relative position of M2 versus M1 is here. And so the relative position here shown by this displacement there, my force on body 2 acting by body 1 is also there. So my displacement's there in this direction, my force acting that part is this way. So we know that there's going to be a net positive internal work done on this part, because the direction cosines here are in the exact same direction. So that means it's a positive work. So that's something you can look at right away, and hopefully we'll see that the math also agrees that we have a positive internal work output there. So now going back to outside the parts, this is our general formula for this internal gravitational force is the minus the universal gravitational constant, the masses, product of the masses divided by the distance between the center of masses of the two parts, and it's in the unit vector r direction, where that's the distance between the center of masses. Definition of work, internal work, so that's the integral of of force dot dr from the initial position to the final position. We know what that force vector is, the magnitude is in there, so we just substitute this value into here, and as we said before, the unit vector r and the dr are in opposite directions. They're there, so we know that's a negative. That dot product. So now solving some more, so we can solve for this. So assuming that this is a constant, masses are constant. My only variable is a function of r, is my r squared. I can take that integral from the initial to the final, and this is what I get. And then I solving an integral, I get a minus and minus, ends up being a plus, which agrees with what we thought before. So it's good confirmation that the math and my force and my displacement are in agreement. And so this is that's always an excellent check one should do, is the force is acting, the displacement in the same direction, then you know that's a positive work. If they were opposite, that'd be a negative work. So the question was gravitational potential energy, not what the work is. Well, a definition of the change in potential energy is minus the internal work. So we had the work was a positive, so the change is a minus. And from the initial to final. If I want to think about now, that just tells me about the change in potential. If I want to consider now what is the absolute value of that potential energy, I could do the instead of the definite integral, the indefinite integral, and I would have this. I'd have the minus the g m1 m2 over r plus some constant. Now, the question is, what's that constant for when the masses are far apart from each other like this? So if r is infinity, okay, so the two masses are infinitely apart from each other, and so at that condition, the gravitational potential energy would be 0. So r infinity, that goes to 0, and so we know this term is 0, so the constant must be 0. So therefore, there really is no constant. So this is the definition then for, well, this is what we've solved as far as the potential energy is being negative, and it's inversely related to r. And now checking it, we know work is the integral of force times the dot product of the displacement. So therefore, work is the integral, force is the derivative. So force is the derivative of the internal work over the d work dr. We know that that internal potential energy and work are one's a negative of the other. So we know that it's minus the derivative of the potential energy with respect to the position. So if I substitute now in my value for the potential energy, which is just that, derivative with respect to r, I can do the math. It ends up being this value right here, which is what we came into the problem with. So that's a good check that the problem was solved correctly. And so this is now, we know this is our relationship for gravitational potential energy when the parts are outside each other. The next thing to do is then let's look at this equation to see what it tells us when the mass is inside the other mass.